Hello, welcome to this video. Today we're going to solve this problem that I came up with. So we need to find all polynomials f with whole number coefficients that satisfy that f of p is a prime number for all p that are prime numbers. So all we know is that f has whole number coefficients and that f of 2 is a prime number, f of 3 is a prime number, f of 4, not f of 4, f of 5, so f of 2, f of 3, f of 5, f of 7, 11, 13, 17, all the primes. If you put them in f, you get back, again, a prime number, and a positive prime number, and negative 3 is not considered one. I'm not sure if that actually matters or not, but I believe it does, so... yeah, it does. So no so a prime, something like negative 7 is not considered a prime. Only positive numbers are considered here as prime numbers. So first of all, let's explain the whole number coefficients thing, because there are polynomials that send whole numbers to whole numbers that don't have whole number coefficients. Take f of x equals 1/2 times x plus 1. If x is a whole number, then it's obviously odd or even. If it's odd, x plus 1 is even and it cancels with the 2 to give us a whole number. If it's even, the x cancels with the 2 to give a whole number. So here the coefficients would be 1/2 for x squared and 1/2 for x, but yet the result is always a whole number for any whole number input. So that whole number coefficients does more than just tell us that every whole number goes to a whole number. And the thing that it actually tells us, that is usually the thing that you should turn to if you see polynomial with whole number coefficients, is the fact that for all whole numbers a and b, a minus b divides into f of a minus f of b. If you see like an Olympiad question with polynomials with whole number coefficients, that's probably the thing you need to look at. You can prove this for yourself. It's pretty easy to prove. I suggest if you try to prove this, first of all, show that a minus b divides into a to the n minus b to the n for every power n that is at least 0, and then you can clearly see why this would be true. So now let's use this. So the way we want to actually get values for f is to get that some number is divides into f of a prime, because f of that prime would be a prime in itself. And then if something divides a prime, then those things are equal. And then we can start getting actual values for the polynomial. So what we're going to do is say, okay, if q is a prime, I know that f of n minus f of q is divisible by n minus q. But I want now, so I want it so that n would be a prime, and that prime I want n to be a prime, and I want this thing to be divisible by f of q. Because then if this was divisible by f of q, so f of q divides into f of n minus f of q, then f of q divides into f of n. And if we choose n cleverly enough such that f of n would also be prime, then we get that f of n, which would be a prime, is divisible by a prime, which would mean they're equal. So the way we're going to do that is like so. I'm going to choose n to be some natural number m, so m is a natural number, times f of q up plus q. Now this would obviously not give a whole number result for every whole number m, but we're just testing here because you will see that this general thing works for half of what we want to do. So if we substitute this n here, we get that f of mf of q plus q minus f of q is divisible by their difference, which is mf of q, but then f of q divides m times f of q. So f of q divides this minus f of q, so f of q divides into f of mf of q plus q. So this always holds. Now I just want to choose q that is a prime number, and m such that this will be a prime number, and m that is an actual number. Well, the thing is, we won't always be able to do that, because what if f of q equals q? Then this would be q times m plus 1, and it would never be a prime number for m that is a natural number, aka at least 1. This would be 2q or 3q and so on. It would never be a prime number. So, but let's assume that there exists a prime q. So now let's suppose there exists a prime q such that q is not equal to f of q. So let's assume, because this holds for every number q, let's assume that there is some prime number q such that this problem does not occur. So what can we do now? Well, we know that f of every prime is a prime number. So if q is prime, so is f of q. And because they're different, that means that f of q and q, they're prime numbers that are different. That means they're co-prime. And if they're co-prime, we can use a theorem about co-prime numbers in these sort of arithmetic sequences. So the theorem is as follows. If a and b are positive and co-prime, and as co-prime I'm going to write that their GCD is 1. Right? That's the standard thing for a and b to be co-prime. Then I can say that there exist infinitely many primes of the form an plus b, where n is a natural number. So if a and b are co-prime, then from this list of numbers, a plus b, 2a plus b, 3a plus b, and so on, this infinite set of numbers, there exists an infinite subset that are just primes. There are an infinite amount of primes that can be described as an plus b. And here what we have, this m can be our n, doesn't matter, just an index. Q and f of q, like we said, they're co-prime, which means that there are infinitely many prime numbers of the form m f of q plus q. So let's take such an m so that this inside here is a prime number. That means that f of this thing is a prime number. Like we said earlier, prime divides a prime, they're equal. Which would mean that f of q equals mf of q plus q. But now, if because there exist infinitely many m's that satisfy this, that means that if we look at the polynomial, the new polynomial, f of x minus f of q, it has infinitely many roots, right? And because there are infinitely many values of m satisfy this, there are infinitely many values like this, mf of q plus q, that satisfy f of them minus f of q is 0. So if a polynomial has infinitely many roots, the only thing it could be is the polynomial 0. So f of x minus f of q is 0, meaning that f of x is a constant f of q. And remember, q is prime, so f of q is a prime. Meaning that, in this case, the only thing that could work is if the polynomial was a prime constant. And indeed, that also satisfies our condition. Because take f of any prime. If f is constant, then f of any prime, heck, any number, would be that prime number, which is prime. Like if f was a constant 7, every prime number would return 7, which is a prime. So that holds. So that works for any prime, meaning that we found actually infinitely many solutions that can be described by f of x equals c, where c is prime. Right? So now we found an infinite family of solutions. F of x is equal to like constant 2, constant 3, constant 5, and so on. So this is one set of solutions. But remember, this is all under the assumption that there exists a prime q such that q is not equal to f of q. Well, so this was actually one case. If we look at the other case, that case says every prime q satisfies that f of q equals q, right? If it's not the case that there is some value q and that there is some prime q such that q is not f of q, that means that every prime satisfies that f of q is equal to q. But now if this is true, that means that if we look at the polynomial f of x minus x, since there are infinitely many prime numbers, that means that this polynomial would now have infinitely many roots. Just like this polynomial here had infinitely many roots. And again, if a polynomial has infinitely many roots, that means it has to be 0. Which means that another solution is that f of x is equal to x, aka the identity polynomial. And you can also see that this works, right? F of any prime, in this polynomial, f of any prime is that prime itself, so f of any prime is just prime. Right? So, and those are the two cases we looked at. They cover the entire spectrum, meaning that these are two solutions. F is the identity polynomial, or f is some prime constant. And that's it. And if you want more content like this, subscribe to my channel. I'll be putting more interesting problems and things like this in the future. And finally, that's it.